All right, section 8.2, we are going to focus on Lewis dot structures. We're going to review doing Lewis dot structures. And then what we're going to focus on is the handful of exceptions that we didn't talk about last year with Lewis dot structures. So we're going to review this real quick because you have a general idea how to do easy Lewis dot structures. If I told you to do the Lewis dot structure for methane, CH4 real quick, all right. CH4, you would go ahead and you'd go C, H, 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 H. Well, let's just go ahead and let's review the rules real quickly for Lewis dot structures, and then we'll kind of continue on with the exceptions. So when we write Lewis dot structures, we have an example here like PCl3. You're going to find the sum of valence electrons for the entire molecule. So if you look on the bottom here, phosphorus has 5 electrons. There are 3 chlorines with 7 electrons. We have a total of 26 electrons. So we have to account for 26 electrons in this compound when we do this. If we have an ion, we're going to add 1 electron for each negative charge. So 1 for -1, 2 for -2. And the exact opposite for cations. If it's a cation, we're going to subtract 1 electron and make it a positive charge. So we'll take 1 away, we'll get +1. Take 2 away, we'll get +2, and on. So step 2. The central atom is the least electronegative element that isn't hydrogen. A lot of times, remember, it's carbon, but if it's not, it's the least electronegative atom. You're going to connect all other atoms to it by a single bond, and you can start with a single bond. You can go to a double or triple if you feel more confident. Remember, we are just kind of reviewing this process. Then you're going to fill the octets of all the other atoms. So of all the outer atoms. So we put in our electrons. We have 6 dots here, 6 dots here, 6 dots here. So we have 18. And then we have 18 with chlorines. And then we have 20, 22, 24. Where do we have to go and find our last pair? Always remember that your last step is going to be filling the octet of the central atom. So there is a real quick, easy example of how we do Lewis dot structures. Now, if you run out of electrons before you get the central atom has an octet, you're going to have multiple bonds. So rather than having these married couples on nitrogen, we're going to throw up, all right, 2 sets like that. All right, now that's kind of backwards from how we did it last year. So do as you feel comfortable with. You guys are, I'm confident in your ability to draw Lewis dot structures. What we have to talk about with Lewis dot structures is what exactly is the right way to draw a Lewis dot structure. So what do I mean by that? Well, there's sometimes you can do multiple ways to draw a Lewis dot structure. For example, if we take carbon dioxide, we have the correct example for carbon dioxide in red. We have an incorrect way of drawing carbon dioxide in blue. Now, technically, the one in blue could work. All right, it could work, but it's not the most correct answer. And when you're drawing multiple Lewis dot structures, there's a couple things that you need to worry about. And that comes in this idea of formal charge. So, formal charge, what's the best way to do this? Well, when we assign formal charge, this is how we're going to assign formal charge. The number of valence electrons it should have. So oxygen, you know, has 6. How many electrons are assigned to it? So we go 6 minus 6, the formal charge is 0. In this example, carbon, how many valence electrons should it have? 4. How many do we have assigned to it? 4. 4 minus 4 is 0. Same thing with our last oxygen over here. It has 6 electrons. Oxygen has 6 electrons. In this Lewis dot structure, we have 6 assigned to it. 6 minus 6 is 0. If you go over to the example that isn't the most correct, what you can see is oxygen should have 6, but we have 7 electrons assigned to it. 6 minus 7 is minus 1. Carbon is 4 minus 4. And then the other oxygen should have 6 electrons, but we only have 5 assigned to it, so its formal charge is plus 1. Now, What's important to note is -1 and +1 will cancel out, so this has a charge of 0, which makes it a good Lewis dot structure. But why isn't it the best Lewis dot structure? Well, when we have the best Lewis dot structure, it's A, the one with the fewest charges. And this slide is very important for the remainder of the year. A, it's the one with the fewest charges. And 2, we put the negative charge on the most electronegative atom. So down below here, we have 3 examples of CNO. 1, 2, and 3. If you look at, and if we wanted to go ahead and kind of practice assigning formal charges, nitrogen should have 5 electrons. However, it has 7 assigned to it, so it has a formal charge of -2. Carbon should have 4 electrons. In this example, it has 4. 4 minus 4 is 0. And oxygen should have 6 electrons, but we only assigned 5 to it in the model, so it's -1. Or sorry, +1, +1, +1, +1. Sorry. So you can see that this has an overall charge of -1, but we have 2 charges. Next up, we are able to eliminate that. Our formal charge on nitrogen's -1. Our formal charge on carbon was 0, and the same with oxygen was 0. The Roman numeral 2 is a better option. Now we go to Roman numeral 3. Again, we have a charge of -1. Our formal charge on nitrogen is 0. Our formal charge on carbon is 0. And our formal charge on oxygen is -1. What makes Roman numeral 3 better than Roman numeral 2? Well, we don't like... All right, let me back up. What makes 3 better than 2 or 1? Well, in example 1, it violates rule number 1, the one with the fewest charges. Roman numeral 1 has 2 charges, -2 and +1, where Roman numeral 2 has 1 solo charge. So we can knock off Roman numeral 1 as not our best option. So now we're down to comparing Roman numeral 2 and 3. Let's go to the next step. We put a negative charge on the most electronegative atom. Well, oxygen is more electronegative than nitrogen, which makes Roman numeral 3 slightly better than Roman numeral 2. All of these are good Lewis dot structures, but we want to focus on having the best Lewis dot structure, and the best Lewis dot structure is Roman numeral 3. All right, now, when we talk about Lewis dot structures, we can talk about a couple things here. Resonance. All right, so if we look at oxygen, and ignore all that writing there. I did not delete that writing from last year. If we look at oxygen, this is a true Lewis dot structure for O3. All right, it's pretty simple. You have O, O, and O. Now, if we look at this, our Lewis dot structure for O3 looked like a double bond, then a single bond. But if we look at actual ozone, what we see is the diagram here. The bond distance between both bonds is the same. Well, how can that be possible if we have a double bond and a single bond? Hypothetically, this bond should be shorter and this bond should be longer because double bonds are shorter than single bonds. But when we look at O3 in real life, we see that the bond length between the O's are equal. Well, how is that equal? Well, it's equal because we have resonance. And what is resonance? Resonance is the sharing, essentially the sharing of the bond. We have this one double bond is flipping, always flipping back and forth. That set is moving. So it's really, ozone could look like this, or it could look like this at any given time. That double bond is continually moving back and forth. So that is what resonance looks like. So what we have is one Lewis dot structure cannot accurately depict a molecule like ozone. We have to draw 2 Lewis dot structures. And you can see the structure on the left and the right is essentially the same, except that double bond is moving back and forth. So we have a pair of electrons that keep moving back and forth when they continue to get shared. And that is resonance. So if we look at another example of resonance, here's kind of the ozone. You have blue, green, and yellow. You can kind of see how ozone is kind of a combination of those two. Don't get caught up on the molecule diagram. But what we have here is resonance, is localized versus delocalized electrons. And localized means the bond is stuck in place. Delocalized means the electrons are moving. Localized means they're in one spot. Delocalized means they can be in many spots. So if we look at another example here of CHO2, we have a resonance structure. You can see that the double bond is moving between carbon and oxygen. In the left-hand example, it is on the rightmost oxygen, right here, and then it moves over to the other oxygen right there, and that is delocalized because those electrons are continuing to move. So that's the idea of resonance. When we talk about resonance from an organic molecule standpoint, you can see benzene. Benzene is C6H6. Benzene has 3 double bonds in its hexagonal structure. So you can see we have one here, and one. All right, one right there. I can't get the marker on it. Sorry, guys. And what happens is then those double bonds shift. What happens is we draw it with a circle to show that those 3 double bonds are always in resonance structure. So those 3 double bonds, there's 3 sets of electrons that are delocalized and always moving to form resonance. So delocalized electrons form resonance. Key thing there. So that is one kind of thing that can happen when we talk about drawing Lewis dot structures. We can have resonance. Also, there are 3 rules, 3 exceptions to the octet rule that we need to follow. All right, number 1. Ions are molecules with an odd number of electrons. So what if we have 25 or 27 or 29 electrons instead of 26 when we did PCl3? There's an exception for that. Number 2, there are molecules with less than an octet rule. And number 3, there are a couple molecules which can have more than an octet rule or an expanded octet. So let's talk in brief about each of those. An odd number of electrons in the outer shell. All right, it's rare to have an odd number of electrons in the outer shell. But if you look at NO, when NO bonds together, you can see we have 11 electrons. Well, how do we do this? Well, you can see that on the left-hand example, we have a double bond. We have 5 electrons on nitrogen, 6 electrons on oxygen. Our formal charge for both of those atoms is 0. And if you look on the right-hand side, it's another acceptable solution where we have 6 electrons on nitrogen and 5 electrons on oxygen. However, if you look at the formal charge, you have +1 and -1 on the right-hand side. So technically, the Lewis dot structure on the left-hand side is the best Lewis dot structure because we have no formal charges on it. So there are odd cases where you can have an odd number of electrons. Next up, fewer than 8 electrons. If we look at BF3, if we go ahead and we look at BF3, what we're going to be left with is boron. Boron has 4 electrons, and it really only wants to give 3 to fully match hydrogen. Then we have that double bond there. So giving boron a filled octet places a negative charge on boron and a positive charge on fluorine, which we don't like to do. So what we will do instead, all right, is its dominant structure is going to be all single bonds. Its less important structure will be the double bonds. So we want to, again, we want to get rid of those. We want to get rid of those formal charges. So the reason is boron only has 6 electrons in its outer shell right there, which is fine because by having 6 in its outer shell, that gives us its most simplest Lewis dot structure. So again, just kind of talking about giving 6 gives it our best Lewis dot structure because we don't have formal charges. Last thing we're talking about, more than 8 electrons. Is it possible for something to have more than 8 electrons? The answer is yes. For example, the molecule down below, we have PCl5 or PF5, can only exist if phosphorus can have 10 electrons around it. And it's allowed to have those extra electrons because presumably you have the d orbitals coming into bond, which usually doesn't happen. Usually only the s and p orbitals bond because those are the only orbitals in the highest energy level. However, sometimes when you get the d orbitals mixing in, it is a possibility to have more than 8 electrons in its outer shell. A prime example is on that Chapter 6 review worksheet. I think we talked about arsenic. We talked about AsF5. How is arsenic bonding? And that way, just like phosphorus is, the d orbital was participating in bonding, which allowed 5 bonds, which allowed 10 electrons in the outer shell. So, same thing though, even though the phosphate ion has only 8 electrons, the better depiction, the better Lewis dot structure ends up being the one with 10 electrons in its outer shell. So you can see here we have left versus right. The Lewis dot structure on the left is an acceptable drawing. It is an acceptable drawing. However, the one on the right is it's a better fit. It's more acceptable. And why is it more acceptable? You have less formal charge. All right. On the one on the left, you have every atom had a charge on it. On the Lewis dot structure on the right, we only have 3 molecules with formal charges. And that is why it's a better Lewis dot structure. It's a better Lewis dot structure because of that. So that kind of sums up Lewis dot structures. It's a concept that gets easy. What you want to focus on is you want to focus on that formal charge. You want to have a Lewis dot structure with the least amount of formal charge. And if you have to have charge, remember you want that charge to go on the most electronegative atom if possible. So that concludes Lewis dot structure.